What if the universe is not empty, but just incredibly patient? 60 years ago, we started listening for alien signals. We have heard nothing confirmed, not once, across thousands of stars and dozens of programs. Most people assume that means we are alone. But in 2017, a small group of physicists proposed a different reading of that silence entirely. Not loneliness, not extinction, optimization. They called it the estivation hypothesis. The logic behind it runs straight through the laws of thermodynamics directly into the Fermi paradox, and it might just be the most terrifying solution to it you aren't ready to hear. If you are new here, subscribe and get comfortable. Because tonight we're going to sit with one of the strangest ideas in science, and by the end, the night sky will never feel quite the same. Let's get into it. Part 1. The silence is not what you think. There is something deeply wrong with the night sky, and most people never notice it. Look up on a clear night, away from city lights, and you will see somewhere between 2,000 and 5,000 stars with the naked eye. That feels like a lot. It feels like abundance. But our galaxy alone contains somewhere between 200 billion and 400 billion stars, and the observable universe contains roughly 2 trillion galaxies. 2 trillion. If you counted one galaxy per second without stopping, without sleeping, without pausing for a single breath, you would be counting for longer than the current age of the universe and still not be done. The numbers are not just large. They're incomprehensible in a way that should genuinely disturb you. And yet, when we listen, we hear nothing. Since 1960, human beings have been pointing radio telescopes at the sky, sifting through electromagnetic frequencies, looking for the kind of structured, non-random signal that a technological civilization would inevitably produce. Project Ozma, the Search for Extraterrestrial Intelligence initiative, what most people know simply as SETI, the Breakthrough Listen project, and dozens of other programs have collectively scanned thousands of stars across decades. The result is one of the most haunting facts in all of science. We have not heard a single confirmed, repeatable, unambiguous signal from another intelligence. Not one. The physicist Enrico Fermi noticed this problem back in 1950, reportedly during a casual lunch conversation, and he asked what has become one of the most important questions in the history of human thought. If intelligent life is statistically likely to be everywhere, then where is everybody? That question, simple, 3 words, devastatingly unresolved, is the Fermi paradox. Most attempts to answer it fall into predictable categories. Maybe intelligent life is extraordinarily rare, a cosmic accident so improbable it happened essentially once. Maybe civilizations inevitably destroy themselves through war, climate collapse, or the invention of technologies they cannot control. Maybe the distances between stars are simply too enormous to ever be meaningfully crossed, even for civilizations millions of years more advanced than us. Maybe they are out there but deliberately avoiding us, the way a hiker avoids disturbing an anthill. Each of these has a name, a literature, a community of researchers who defend it. But in 2017, a group of physicists proposed something different. Something that does not fit neatly into any of those categories because it does not assume failure, extinction, or avoidance. It assumes success. It assumes that intelligence, when it becomes truly advanced, behaves in a specific and predictable way, a way governed not by culture, not by psychology, not by the accident of evolutionary history, but by the fundamental laws of physics themselves. The hypothesis is called the estivation hypothesis, and it was put forward by Anders Sandberg, Stuart Armstrong, and Milan Ćirković. The word estivation comes from biology. You may have heard of hibernation, the winter sleep of bears and groundhogs. Estivation is the summer equivalent, a state of dormancy triggered not by cold, but by heat and drought. Certain snails, lungfish, and desert amphibians enter a metabolic slowdown when their environment becomes too hot or too dry to sustain normal activity. They do not die. They do not flee. They simply wait for conditions to improve, sometimes for years, and then they wake up and continue as if nothing happened. Sandberg, Armstrong, and Ćirković took that biological concept and applied it to something almost unimaginably larger. Their argument stated plainly is this: advanced civilizations are not absent from the universe. They are not extinct, not hiding, not travelling, not avoiding us. They are waiting. Not because they are patient in some poetic, metaphorical sense, but because waiting is the computationally optimal strategy given the known physical laws governing how information processing works. They have paused, deliberately, the way a computer enters sleep mode, and they are sitting in a low-activity state conserving their resources until the universe reaches a condition in which those resources can be used with vastly greater efficiency. The silence we hear when we point our telescopes at the sky is not absence. It is the sound of intelligence behaving rationally. That is either the most elegant solution to the Fermi paradox ever proposed, or it is one of the most disturbing ideas in the history of science. Maybe both. But to understand why it might actually be correct, we need to talk about a law of physics that most people have never heard of, a law discovered not by an astronomer or a cosmologist, but by a computer scientist working at IBM in 1961. And once you understand that law, the silence of the universe will never feel the same again. Part 2. The law that changes everything. Rolf Landauer was not thinking about alien civilizations when he published his paper in 1961. He was thinking about computers, specifically about a question that had been nagging at physicists for years. Does thinking cost energy? Not in the vague sense that running a brain requires calories. In a precise, fundamental, unavoidable physical sense, does the act of processing information leave a thermodynamic footprint on the universe? His answer was yes, and the reasoning behind it changed how we understand the relationship between information and physical reality. The key insight is about erasure. When a computer, or any information processing system, erases a bit of information, that operation is logically irreversible. You had a 1 or a 0, and now you have just a 0, and the record of which it was is gone. Landauer showed that this irreversibility has a physical cost. Every time you erase one bit of information, you must release a minimum amount of energy into the surrounding environment as heat. That minimum is given by a precise formula involving two constants of nature. The Boltzmann constant, which connects temperature to energy at the molecular scale, and the natural logarithm of 2, which comes from the binary nature of the bit. Together they produce what is now called the Landauer limit, and it states that the minimum energy cost to erase one bit is equal to the temperature of the environment multiplied by the Boltzmann constant, multiplied by the natural log of 2. This is easy to state. The implications take longer to absorb. The critical variable in that formula is temperature. The minimum energy required to perform a computation is directly, linearly proportional to the temperature of the surrounding environment. This is not an engineering challenge that cleverer hardware can overcome. This is not a limitation of silicon or software. This is the physics of reality. The hotter your environment, the more expensive every single computational operation is, by law, with no exceptions. And now here is where the universe enters the picture. Right now, the universe has a baseline temperature. Even in the coldest, emptiest region of space, far from any star or galaxy, there is a faint background radiation filling every corner of existence, a leftover thermal glow from the Big Bang. This is the cosmic microwave background, and it currently sits at about 2.7 Kelvin. For reference, absolute zero, the theoretical point at which all thermal motion stops, is 0 Kelvin. 2.7 Kelvin is extraordinarily cold by any human standard, but it is not zero. And because it is not zero, it still imposes a computational cost on any system operating within the universe today. But the universe is expanding, and as it expands, it cools. The cosmic microwave background has been dropping in temperature since the moment of the Big Bang, and it will continue to drop. asymptotically approaching but never quite reaching absolute zero for as long as the universe exists. Billions of years from now, trillions of years from now, the background temperature of the universe will be orders of magnitude lower than it is today. Here is what that means for computation, and follow this carefully because it is the engine of the entire estivation hypothesis. If you have a fixed reserve of energy, a battery, a fuel source, a supply of mass that can be converted to power, then the number of computations you can perform with that energy is inversely proportional to the temperature of your environment. At today's temperature of 2.7 Kelvin, you can perform a certain number of operations per joule. At 1/10 of that temperature, you can perform 10 times as many operations per joule. At 1/100th of that temperature, 100 times as many. The relationship is direct and unforgiving. Sandberg and his collaborators ran the numbers for how much the universe will cool between now and the far future. And the result is one of those figures that requires you to sit quietly for a moment before you continue. The efficiency gain available by waiting for the universe to cool, the increase in computations per unit energy between the present era and the coldest accessible future era, is on the order of 10 to the power of 30. That is a 1 followed by 30 zeros. A nonillion, if you prefer a word for it, though the word does not really help. Let me try to give you a feel for that number. If you have 1 joule of energy right now, and you use it to perform computations, you get some number of operations. Call it 1. If you instead stored that joule, did nothing with it for an almost incomprehensible span of time, and then spent it in a much colder future universe, you would get not 2 times as many operations, not 1,000,000 times as many, not 1,000,000,000 times as many. You would get 1,000,000 trillion times as many operations from the exact same joule of energy. Thinking now in this warm young universe is extraordinarily wasteful. Thinking later, in the cold, dark future, is extraordinarily efficient. For a civilization that has access to this knowledge, and any civilization significantly more advanced than us would certainly have it, this creates a calculation with an answer that is not ambiguous and not culturally relative. It is simply the rational thing to do, the way that investing money at compound interest is the rational thing to do, compared to burying it in your backyard. And that calculation is pointing directly at the silence in our sky, which makes the question that follows both obvious and a little terrifying. If the math so clearly favours waiting, how many civilizations have already done the arithmetic? Part 3. The first terrifying realization. Let us think through what the Landauer argument actually predicts about civilizations, because the logical chain from here moves fast and it lands somewhere genuinely strange. If waiting dramatically improves computational efficiency, and if a sufficiently advanced civilization has the ability to store its energy reserves, maintain its infrastructure in a low-power state, and protect itself from threats over very long timescales, then a rational superintelligence does not spend its energy now. It conserves, it waits. It enters something like a hibernation state, minimizing all activity that is not strictly necessary for the preservation of its resources and the basic structural integrity of whatever systems it needs to eventually wake up and operate. The civilization still exists. Its accumulated knowledge, its stored computational substrate, its energy reserves, all of it is preserved. But from the outside, from the perspective of another civilization trying to detect it, it produces almost nothing. No large electromagnetic emissions because it is not running its computational infrastructure. No major waste heat signatures because it is not consuming significant energy. No engineering projects because it is not actively building anything. No signals because it has no reason to broadcast. It is, for all practical purposes, invisible. And here is the thing that reshapes the entire Fermi paradox in one move. If this is the behavior of advanced civilizations, then what we have been interpreting as evidence that advanced civilizations do not exist is actually fully consistent with the hypothesis that they do exist, but are simply not doing what we expected them to be doing. We built our expectations based on ourselves. We are a young, active, energetic, expanding civilization that broadcasts electromagnetic radiation more or less continuously from our radio stations, our television transmitters, our radar systems, our communication satellites. We glow in the radio spectrum, we make noise, we build things. We are the cosmic equivalent of a toddler banging pots together in a kitchen, and we looked out at the universe and said, surely the adults are doing the same thing, just louder. But what if the adults are not banging pots? What if they stopped that phase of development millions of years ago and moved on to something quieter? There is an uncomfortable hierarchy that emerges from this logic, and once you see it, you cannot unsee it. Active civilizations, the ones making noise, sending signals, building things, expanding across their stellar neighborhoods, these are the young ones, the immature ones, the ones still spending their computational budget inefficiently because they have not yet lived long enough to appreciate what patience is worth, or perhaps because they have not yet accumulated enough resources to afford to wait. The civilizations that have been around long enough, that have done the math, that have accumulated what they need, they go quiet. Progress in this framework looks like silence. Advancement looks like disappearance. This means SETI, as it has been practiced for 60 years, may have a fundamental flaw in its design. SETI listens for the signatures of active, expansionist, energetically promiscuous civilizations, the kind that broadcast, the kind that build megastructures that glow in the infrared, the kind whose presence can be inferred from their emissions. But if the aestivation hypothesis is correct, then SETI is specifically calibrated to detect the early-stage civilizations, the ones that have not yet made the rational decision to go dormant. Every null result from SETI does not tell us the galaxy is empty. It tells us the galaxy is quiet. And those are very different things. Think about what it would mean to be surrounded right now by intelligence. Not distant intelligence, not intelligence tucked into some far corner of the galaxy, but intelligence distributed across our cosmic neighborhood, stored, waiting, managing its energy, counting down across trillions of years toward a future where it can finally unleash the computation it has been saving. Not aware of us, not interested in us, not ignoring us out of contempt. Simply in a different phase of existence, the way a seed buried in the ground is not absent from the meadow. It is just waiting for conditions that do not yet exist. We might be early. That possibility is not comforting in the way it might first seem, because being early means being alone in a universe that is already decided. It means the silence around us is not a sign of a clean slate, but a sign of a game whose opening moves were played long before our sun was born, and the question of what those opening moves looked like, and what they mean for anyone who arrives later, that is where things get interesting. Part 4. The Cosmic Thermostat. The universe began hot. Incomprehensibly, almost beyond physics hot in the first fractions of a second after the Big Bang, when all the energy that currently fills the observable universe was compressed into a space smaller than an atom. From that point, the story of the universe has been, in thermodynamic terms, one long cooling curve. Expansion carries energy, but it also spreads that energy thinner and thinner across an ever-increasing volume of space, and the result is a universe that has been dropping in temperature for 13.8 billion years, and will continue to do so for longer than we have good language to describe. The cosmic microwave background is the most direct record of this cooling. When the universe was about 380,000 years old, it had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time, a moment cosmologists call recombination. Before that, the universe was opaque. Photons could not travel freely because they were constantly scattering off the dense soup of charged particles. After recombination, the universe became transparent, and those photons streamed outward in every direction, carrying the thermal imprint of that moment. We can still detect them today, after billions of years of expansion, redshifted from visible light all the way down to microwave frequencies, arriving at our detectors from every direction equally, a ghost signal from the first clear moment of the universe. When the universe was 380,000 years old, that background radiation had a temperature of roughly 3,000 Kelvin, about the surface temperature of a dim red star. Today, after 13.8 billion years of expansion, it sits at 2.7 Kelvin. The universe has cooled by more than a factor of 1,000 since the first photons travelled freely, and it is not done cooling. The relationship between the expansion of the universe and the temperature of the cosmic microwave background is a precise one. As the universe expands, the wavelengths of those background photons stretch proportionally, and longer wavelengths correspond to lower temperatures. The universe will continue expanding, almost certainly accelerating in its expansion due to dark energy, and the background temperature will continue to fall. The cooling is not linear, it follows the expansion rate, but it is relentless. Here is what that means for the estivation hypothesis, and this is the direct connection that makes the physics more than just interesting background. Every time the background temperature of the universe drops, the Landauer limit drops with it. Every time the Landauer limit drops, the efficiency of information processing improves. Every joule of stored energy becomes more computationally valuable. The universe is not just expanding into cold emptiness. From the perspective of an information processing system, a mind, a computer, a civilization, the universe is on a slowly improving trajectory, a long upward curve in the efficiency of thought, driven by nothing more exotic than the natural physics of expansion and cooling. The universe is, in a very real sense, a computer that is becoming more powerful every second, not by acquiring new hardware, but simply by cooling down. And if you have the patience to wait, if you can survive long enough, if you can store your energy and maintain your systems across timescales that dwarf the current age of everything, then you can access that improvement. The universe is offering a deal, and the terms of the deal get better every passing trillion years. The question is whether you can afford to wait for the terms to mature, and what it would mean about where everyone else has gone if they already said yes. Part 5. The future is worth more than the present. There is a concept in economics called the time value of money, the idea that $1 today is worth more than $1 tomorrow, because $1 today can be invested and will earn interest. The version of this principle that applies to intelligent civilizations operating across cosmic time is almost the exact inverse, and that inversion is fundamental to the estivation hypothesis. Energy in the future is worth more than energy today, in terms of computation. Not slightly more, astronomically more. When Sandberg and his colleagues put the number at 10 to the 30, they were describing what in economic terms would be called an extraordinary rate of return. If you imagine a civilization's stored energy reserves as a kind of cosmic savings account, the interest rate on that account is not a few percent per year. It is the difference between spending $1 now and spending it in a future era where $1 buys a nonillion times more goods. There is no rational economist who, given that exchange rate, would recommend spending today. Let us try to build an intuitive bridge to the scale of what 10 to the 30 actually means for intelligence. Every thought you have right now is occurring at the thermodynamic cost dictated by the current temperature of the universe. The neurons firing in your brain, the electrical signals crossing synaptic gaps, the molecular machinery of memory and attention, all of it is happening in an environment that has a temperature, and that temperature sets a floor on how efficiently those operations can occur. A civilization running its central computational infrastructure in the present era is paying the same kind of premium. It is doing real thinking, real processing, real intellectual work, but it is paying a tax on every operation, not in money, but in wasted computational potential relative to what those same joules could have purchased if spent later. Now imagine a civilization that has been around for 200 million years, which in the context of the universe's 14 billion year history is not even particularly old. A civilization that old would have had time to do the physics, to understand Landauer's principle, to calculate the efficiency curves, and to make a decision. That decision, rationally, looks like this. Stop running the expensive operations, preserve the infrastructure, store the energy, activate the long-term maintenance systems, set a wake-up condition tied to some future temperature threshold, and then wait. What would be waiting for? Not just for things to get cheaper in some vague sense, for a specific calculable point at which the universe's background temperature has fallen far enough that the stored energy reserve can be spent with maximum efficiency, producing the maximum possible computation, the maximum possible thought, experience, memory, problem-solving, creativity that the laws of physics permit. This is what makes the estivation hypothesis so different from other Fermi paradox solutions. It does not invoke extinction, failure, catastrophe, or cosmic loneliness. It invokes optimization. It says that what looks like the universe's emptiness might actually be the universe's maturity, that the civilizations we are not hearing from are not dead. They are saving up. They are waiting for the best possible time to exist, fully and richly, in a way that our current era simply cannot support as efficiently. And if that is true, then we are not looking at a graveyard when we look at the sky. We are looking at a dormant system, something waiting for the moment when conditions justify waking up, which leads naturally to what that moment would actually look like and what the universe will be when it arrives. Part 6. The Deep Future. Imagine the universe not as it is today, but as it will be in approximately 10 to the power of 14 years, 100 trillion years from now. That number needs a bit of anchoring. The current age of the universe is roughly 13.8 billion years, which is 1.38 times 10 to the 10th. We are talking about an era that is more than 7,000 times older than the universe is right now. By that point, something fundamental will have changed. Stars will be mostly gone. Today, the night sky burns with billions of stars in every direction. Nuclear furnaces converting hydrogen into helium and bleeding light and heat across thousands of light years. Stars are prodigiously wasteful from a computational perspective. They're enormous masses of energy radiating freely into space, doing no useful work for any information processing system. But stars have lifetimes. Low-mass red dwarf stars, the longest-lived stellar type, will burn out in several trillion years. After that, the era of star formation will be effectively over. The raw hydrogen fuel for new star formation will have been consumed or locked up in remnants. What will remain is a universe dominated by stellar corpses, white dwarfs slowly cooling across geological timescales, neutron stars spinning down their rotational energy over billions of years, and black holes, patient, massive, extraordinary repositories of gravitational energy, the densest objects the universe permits, slowly evaporating via Hawking radiation over timescales that are essentially incomprehensible. A stellar mass black hole will take roughly 10 to the 67 years to evaporate. A supermassive black hole, the kind that anchors galaxies today, might take 10 to the 100 years to fully radiate away. These timescales make 100 trillion years look like an eye blink. But here is what that era means for a waiting civilization, and this connects back to the central argument in a direct way. The cosmic microwave background in that future era will be at a temperature so low that it effectively rounds to zero on any scale that matters for daily experience. The background will be something like 10 to the negative 8 Kelvin, 100th of a millionth of a Kelvin. At those temperatures, the Landauer limit on computation cost is 100 million times lower than it is today. Every joule of energy will buy 100 million times more computation than it buys right now. A civilization that has stored its energy and waited for that era to arrive wakes up into a universe where thinking is almost free, where the computational budget it has been preserving across hundreds of trillions of years suddenly has the purchasing power of a king, where the ideas it has been unable to process, the simulations it could not afford to run, the problems it could not justify solving at today's prices, all of that becomes accessible. This is the computational awakening. This is what the waiting is for. It changes how we should read the present era of the universe. If this picture is right, then everything happening today, every star forming, every galaxy colliding, Every civilization that might be arising, including ours, is occurring in what might be called the preparation phase of the universe. The hot, noisy, energetically extravagant early epoch, before the cooling has done its work, before the real computation begins. From the perspective of a civilization designed to thrive in the deep future, the present universe is prehistory. The interesting events have not happened yet, and we are here now, looking out at a universe that may already be managed, already organized, already pre-planned for a future that will not begin for timescales we can barely gesture at. How that management happened and what it looked like is a different kind of story and a harder one to tell. Part 7. Invisible Megastructures. In 1960, the physicist Freeman Dyson wrote a paper that changed how people think about advanced civilizations. He proposed that a sufficiently advanced civilization, needing more energy than a single planet's surface could collect, would eventually build a structure around its star, a shell or a swarm of structures that intercepted the star's entire energy output. Dyson was not writing science fiction. He was doing engineering speculation grounded in thermodynamic necessity. A civilization growing in population and complexity would eventually need more power than its home planet could provide, and the star it orbited was the obvious source. These structures, now called Dyson spheres or Dyson swarms, became the foundational concept behind one branch of SETI. If you cannot detect a civilization's radio signals, maybe you can detect the waste heat from its megastructure. A Dyson sphere absorbing a star's light output and converting it to computation would still have to radiate the waste heat somewhere, Landauer's principle again, operating as an inescapable tax on all information processing. That waste heat would emerge in the infrared spectrum at temperatures characteristic of the megastructure's operating temperature. Between 2011 and 2014, a project called the Glimpsing Heat from Alien Technologies survey, sometimes called GHAT, surveyed approximately 100,000 galaxies looking for exactly this kind of anomalous infrared signature. They found nothing conclusive. But here is what those null results cannot rule out, and this is where the estivation hypothesis intersects with the megastructure question, in a way that makes the silence make sense. A dormant megastructure produces almost no waste heat. If a Dyson sphere has been placed into low-activity maintenance mode, if the civilization running it has chosen to minimize operations, store energy rather than spend it, and wait out the current warm era of the universe, then its infrared signature would be negligible. It would not glow in the way GHAT was searching for. It would sit there, massive, engineered, extraordinary, and nearly invisible precisely because it was doing exactly what its builders designed it to do: conserve. The GHAT survey was looking for civilizations that are actively running their infrastructure at high power. It was listening for the noise of operation, but a civilization that has completed the transition to estivation has deliberately minimized that noise. The absence of infrared signatures tells us that there are no active high-powered megastructures in those 100,000 galaxies. It tells us very little about whether dormant ones are there. And that asymmetry in what our instruments can and cannot detect is not a minor technical footnote. It is the difference between evidence of absence and the absence of evidence, two things that are not the same. Part 8. The Architecture of Sleeping Gods. If you wanted to design a civilization for long-term dormancy, what would it look like? This is not a question any engineer has seriously had to answer, but it is one that follows logically from the estivation hypothesis, and working through it tells us something about what we might be failing to detect. One concept that has circulated in theoretical discussions of advanced civilizations is what the physicist Robert Bradbury called a matryoshka brain, a set of nested computational shells surrounding a star, each layer capturing the waste heat from the layer inside it, and using that energy for additional computation before radiating it onward, extracting maximum computational value from every joule the star produces. This is the active version, the high-efficiency architecture for a civilization in full operation. But in a dormant state, A matryoshka brain would be a different kind of structure entirely. The shells would be present, the infrastructure would be in place, but the processing would be throttled to a minimum, just enough to maintain system integrity, monitor for threats, manage the stored energy reserves, and keep the wake-up systems operational. From outside, in the present era, this would look like a star with unusual spectral properties, perhaps, or a region of space with subtly anomalous energy distributions. But the signal would be quiet, intermittent, and easy to dismiss as natural astrophysical variation if you did not already know what you were looking for. Then there are black holes. Physicists have theorized about black hole computing since the work of Jacob Bekenstein in the 1970s, established that black holes carry entropy proportional to their surface area. A civilization that understood this could potentially use the extreme gravitational and informational properties of black holes as ultra-dense computational substrates, storing maximum information in minimum space. For a civilization going dormant, a black hole might serve as the ultimate long-term storage medium, a place to park information and energy in a form that will survive essentially intact for timescales, far exceeding the lifetime of any star. The civilization's knowledge, its accumulated experience, its prepared computational programs, all of it compressed into a structure that will outlast the universe's current epoch by many orders of magnitude and remain available for retrieval when the time comes. Combine these possibilities: dormant matryoshka shells maintaining energy reserves, black hole information storage, distributed maintenance networks spread across stellar systems, and you get an image of what a sleeping superintelligence might look like in physical terms. Not a blazing, electromagnetic loud presence. A quiet, thermodynamically optimized infrastructure holding pattern, waiting. Undetectable by our current instruments, because our current instruments are designed to find the opposite of what it is doing. This is not a dismissal of SETI. It is a reframing of what SETI is actually measuring and what its results actually mean. And that reframing connects back to the central silence in a direct way. We are not detecting absence. We are potentially failing to detect a presence that has specifically organized itself to not be detected during this era. Part 9. The void is not empty. There is a structure in the universe that has bothered cosmologists since its discovery in 1981, and it goes by the name of the Bhuta's void. It is a region of space roughly 330 million light-years in diameter, located in the direction of the constellation Bhuta's, and it contains almost nothing. Where the standard distribution of galaxies across the universe places clusters and filaments and walls of galactic material separated by regions of relative emptiness, the Bhuta's void is something different, an underdensity of galaxies so extreme that it caught astronomers off guard when they first mapped it. You would expect to find roughly 2,000 galaxies in a volume that size. Instead, there are about 60. Standard cosmology has explanations for this. Structure formation in the early universe, driven by quantum fluctuations in the density of the primordial plasma and amplified by gravitational collapse over billions of years, naturally produces a web-like architecture, the cosmic web, with galaxy-rich filaments and relatively empty voids between them. The Bhuta's void, in this telling, is simply an unusually large example of a normal cosmological feature, the product of statistical variation in how the universe's matter distributed itself after the Big Bang. This is almost certainly the correct explanation. But the estivation hypothesis opens a door to a different kind of curiosity, and it is worth walking through it for a moment, not as a serious scientific claim, but as a thought experiment that illustrates something important about the limits of our knowledge. What would a region of space look like after an advanced civilization had completed its energy harvesting phase? After it had collected the resources it needed for its long dormancy, consolidated its energy reserves, and transitioned to a low-activity maintenance state? One answer is that it might look like a region with fewer actively burning stars than cosmology would predict, because stars that have been incorporated into energy harvesting megastructures are no longer visible as stars in the conventional sense. It might look like a region with anomalous large-scale structure, because the civilization's engineering projects operated at scales that left traces in the distribution of matter. It might, in some extreme scenario, look like a void, not because it is empty, but because its energy has been organized in a form that no longer emits in the frequencies we use to map galactic structure. Is the Bhuta's void the remnant of a cosmic civilization's harvest? Almost certainly not. The mainstream explanation is sufficient, and extraordinary claims require extraordinary evidence that does not exist here. But the thought experiment is instructive because it illustrates the fundamental epistemic problem. We map the universe using its emissions. We find structure where things are glowing and emptiness where they are not. But a dormant, thermodynamically optimized intelligence would specifically minimize its emissions. Our map of the universe is a map of light, and light is what the estivation hypothesis predicts the waiting ones are not producing. Part 10. First in, last out. In 2018, a Russian physicist named Alexander Berezin published a short paper with a title that does not try to soften the blow. He called it First in, Last out, and before we even get into the argument, I want you to notice something about that title. It does not say first in wins. It does not say first in dominates. It says last out. As in, everyone else exits before the first one does. As in, the story ends for everyone except whoever got there first. That framing is not accidental, and by the time we work through the logic, you will understand exactly why Berezin chose those words. His starting point is the Fermi paradox stated without softening. The universe is old. The universe is large. The chemistry of life is not exotic: carbon, hydrogen, oxygen, nitrogen, the four most common reactive elements in the cosmos, assembling into amino acids in interstellar clouds, arriving on planetary surfaces inside meteorites, doing the patient work of complexity over hundreds of millions of years on world after world after world. The expectation that intelligence has arisen elsewhere is not wishful thinking. It is a straightforward reading of the numbers, and yet the sky is quiet. There are no confirmed signals. There is no unambiguous evidence of engineering at cosmic scales. There is nothing that requires the presence of another mind to explain. The paradox is real, Berezin says, and it demands a real answer, not a statistical shrug. His proposed answer is one of the more uncomfortable ideas in the Fermi paradox literature, and what makes it uncomfortable is not that it is violent or cruel. It is that it does not need to be either of those things to arrive at its conclusion. The argument works through ordinary logic, the kind that requires no malice, no conspiracy, no directed effort of any kind. It requires only the structural consequences of being first. The first civilization to achieve genuine interstellar travel, not theoretical interstellar travel, not generation ships crawling between stars over thousands of years, but practical, scalable, self-replicating expansion across stellar systems. That civilization begins a process that cannot be undone and cannot be shared. It starts using the galaxy. It consumes stellar energy to power its expansion. It processes raw materials from asteroid belts, planetary surfaces, the debris fields around stars. It establishes infrastructure in the most resource-rich and strategically valuable locations. And crucially, it does all of this not out of hostility toward anything else, but simply because these are the resources available, and this is what expansion requires. Here is the analogy Berezin offers, and I want to stay with it for a moment because it is doing a lot of work. When a construction crew moves in to build a parking lot on a vacant piece of land, they do not walk the site first looking for ant colonies. They do not conduct an environmental impact study on the local insect population. They grade the earth, pour the concrete, and build the parking lot. If there were ant colonies on that land, those colonies are gone now, not because anyone targeted them, not because ants were perceived as a threat, not because there was any decision made about ants at all. The ants were simply not a factor in the calculation. They were irrelevant to the process that eliminated them. That is the mechanism Berezin is describing, and the reason it is harder to dismiss than a straightforward "they destroyed everyone" scenario is precisely because it requires no decision. A civilization that intentionally hunts down competitors has to first become aware of them, then develop a strategy, then execute it across potentially thousands of light years. That is a complicated chain of causation with many places it could fail or not occur. But a civilization that simply expands because expansion is what expansionary civilizations do, using resources because resources are what expansion requires, does not need to be aware of anything else. The filter operates automatically, structurally, as a byproduct of normal development. Now apply this at galactic scales and follow the logic forward across time. The first civilization to go interstellar begins spreading outward from its home system. Each new system it inhabits becomes a base for further expansion. The frontier advances outward in an expanding sphere, incorporating star after star, reorganizing each system's resources into the civilization's infrastructure. This process, driven by exponential growth in the number of inhabited systems, does not take forever. At even a modest fraction of the speed of light for expansion probes or self-replicating systems, a civilization could spread across a galaxy the size of the Milky Way in somewhere between 1 million and 100 million years. That sounds long, but the galaxy is over 13 billion years old. The window for this to have already happened, long before our sun ignited, is enormous. As the expansion proceeds, the resource landscape of the galaxy changes. The star-forming regions most likely to produce habitable planets and eventually technological civilizations are the same regions most attractive to an expanding civilization seeking energy and raw materials. The long-lived stable stars best suited for nurturing intelligent life over billions of years are exactly the kind of stars worth incorporating into an expanding civilization's network. The chemical and energetic prerequisites for life to develop elsewhere are in large part the same prerequisites that expansion consumes, not maliciously, just structurally. What this means is that the window during which a second civilization could arise, develop technology, and begin its own independent expansion may close before that second civilization ever gets started. The developmental timeline for intelligence is long, 4 billion years on Earth, from the first single-celled life to a species that can build radio telescopes. An expanding first civilization, reorganizing the galaxy's resources across millions of years, may have closed the relevant windows long before any second civilization reached the point of technological relevance. Not because it was watching for competitors, because it simply moved through the galaxy the way weather moves through a landscape, reshaping everything it touched without awareness of what that reshaping cost. This is where Berezin's argument lands, and this is why the title says last out rather than first wins. The first civilization does not triumph over rivals. There are no rivals in any meaningful sense. There is one civilization that expanded when expansion was possible, and then there is everything else, every other potential intelligence that might have arisen, that was developing along its own timeline, that never reached the finish line because the conditions for reaching it were reorganized before it could get there. The first one does not leave. Everyone else does. And now connect this back to the silence, because that connection is the reason this idea matters for our purposes. If Berezin is right, then the galaxy we live in is not a neutral, open, undeveloped territory waiting for whoever arrives first. It is a territory that has already been organized. The expansion phase in this picture ended a very long time ago. What followed, and what we are living inside right now, is the quiet aftermath of a process that completed before our sun existed. The house is not empty. It has been closed up for the season, the lights off, the systems in maintenance mode, the occupant somewhere inside in a state that produces no detectable emissions and no reason to knock on the door. The quiet of the galaxy, in Berezin's framing, is not the quiet of absence. It is the quiet of completion. Something got there first, did what first arrivals do, and the universe reorganized around that fact so long ago that we have no record of it, no witness, no trace that is legible to us with our current instruments. We are the ant colony that formed in the parking lot's expansion joint, looking up at the concrete sky and wondering where all the other animals went. They were here. They just were not factors in the calculation. And what happened after the expansion ended, what the first civilization actually did with all those resources once the galaxy was reorganized around its needs, that is where the story takes the turn that changes everything. Part 11, Why There Can Only Be One. The mathematics behind why only one civilization might come to dominate a galaxy are not exotic or unfamiliar. You've seen this pattern before, just at smaller scales. It shows up in biology, in economics, in the history of technology adoption, in the way that one social media platform absorbs the attention of 1 billion people while its competitors fade into irrelevance. Exponential growth in a bounded system tends to produce a winner, not through conspiracy, not through superior virtue, not even necessarily through superior capability, but through the compounding arithmetic of an early advantage applied to a growth curve steep enough that late entrants cannot close the gap. What makes the galactic version of this pattern different is not the mechanism. The mechanism is the same one that produced every monopoly in human economic history. What makes it different is the scale at which the compounding operates, and the degree to which that scale makes the outcome not just likely, but mathematically inescapable in a way that smaller systems are not. Let us work through what interstellar expansion actually involves, concretely, because the abstraction of exponential growth can feel weightless until you fill it in with specifics. A civilization develops the ability to send a self-replicating probe, or a seed ship, or some form of von Neumann device to a neighbouring star system. That probe arrives, uses local resources to establish a presence, builds the infrastructure necessary to support habitation or computation or further expansion, and then launches the next generation of probes outward to the next ring of stellar systems. Each system reached becomes a new launch point. The expansion does not wait for instructions from the home system, because the communication lag across light years makes centralized control impractical. Each node in the network operates with some degree of autonomy, doing what expansion nodes do: arrive, establish, launch. Now count the systems. In the first generation of expansion, the civilization reaches the handful of star systems nearest its home, perhaps 4 or 5 within a few light years. In the second generation, each of those systems launches probes of its own, reaching the systems nearest to them, which may overlap somewhat with already claimed territory, but mostly extends the frontier outward. In the third generation, the frontier extends further still, the number of newly claimed systems larger again. This is not a linear process. It is a branching, accelerating wave, and the number of systems under the civilization's influence at any given moment scales not with time, but with time raised to a power. The frontier does not advance, it explodes. A civilization that began this process 5 million years before any competitor, which in galactic terms is an eye blink. Our sun is 4.6 billion years old, so 5 million years is roughly 0.1% of stellar lifetime, would, by the time the competitor launched its first interstellar probe, already have organized a sphere of influence potentially spanning thousands of light years in every direction. Thousands of star systems incorporated into its resource network. Thousands of energy sources tapped, raw material reserves processed, strategic locations secured. The second civilization launches its first probe into a galaxy that is no longer open. It is launching into a galaxy that has already been organized around someone else's needs. And the systems it might have expanded into, the energy-rich stars near the galactic center where stellar density is highest, and expansion opportunities most abundant, the stable, long-lived stars most suitable for long-term habitation, the asteroid belts and planetary systems richest in the raw materials that interstellar infrastructure requires, all of it is already spoken for. Not necessarily occupied in any dense or visible sense, but incorporated, part of someone else's network, already serving a function in someone else's economy. Think about what that means in practical terms for the second civilization. It is not starting from zero in a pristine, open universe. It is starting in an environment where the most valuable resources have already been allocated, where the most strategic positions have already been claimed, where every direction it might expand is already inside the sphere of influence of a civilization that has been growing exponentially for 5 million years, longer than it has existed. The gap is not a gap it can close. The gap is a structural feature of the situation it was born into, and it compounds with every passing year. There is a temptation to imagine that two spacefaring civilizations might negotiate, divide the galaxy peacefully, establish a boundary, a treaty, a mutual recognition of each other's spheres, and perhaps in some scenarios that is possible, but it requires that the second civilization develop the capability to negotiate from a position of relevance before the first civilization's expansion has made that relevance impossible to establish. It requires a specific timing, late enough that both civilizations exist simultaneously, early enough that the resource landscape has not yet been fully organized. That window may be extraordinarily narrow. Given how long the galaxy has been around and how early the first expansion could theoretically have begun, that window may have already closed billions of years ago. What the physics of expansion actually produces is not equilibrium. It produces monopolization. Not inevitably through violence, though the history of human civilizations expanding into territories occupied by others does not offer much comfort on that point. But even setting aside conflict entirely, even imagining a perfectly peaceful first civilization with no interest in harming anyone, the arithmetic produces the same result. One civilization with a head start in exponential expansion will, through the sheer compounding of its advantage, come to occupy the resource landscape of the galaxy in a way that forecloses independent expansion by anyone who comes later. The galaxy becomes, structurally, a single civilization system, not by decree, by math. And now here is where this connects back to the central argument in a way that matters, because the winner-take-all dynamic is not the end of the story. It is the setup for the next chapter, a civilization that has completed the consolidation of a galaxy's resources faces a different problem than the one it started with. Expansion was the challenge when resources were distributed across thousands of unincorporated systems, and the imperative was to reach them before conditions changed. But once the incorporation is complete, once the network spans hundreds of thousands of light years and the major resource pools are secured, expansion stops being a rational strategy. It becomes an expensive habit. Consider the cost of maintaining a galactic-scale infrastructure. Every node in the network requires energy to operate. Every communication relay, every monitoring system, every piece of engineering distributed across the civilization's vast sphere of influence draws on the energy budget. Managing that infrastructure actively, running it at high power, keeping every system fully operational, maintaining the kind of energetic footprint that a maximally active galactic civilization would produce, is extraordinarily expensive in exactly the terms that the Landauer argument makes relevant. It burns through computational and energetic resources at a rate that is thermodynamically irrational, given what those same resources could purchase in the cold far future. A civilization smart enough to have conquered a galaxy is certainly smart enough to have done the physics. It understands Landauer's principle. It has calculated the efficiency curves. It knows, with the precision that only a civilization millions of years more advanced than us could bring to the calculation, exactly how much more its stored energy will be worth in a universe 10 degrees colder, 100 degrees colder, 1,000 degrees colder. And it knows that every joule spent maintaining an active galactic infrastructure right now is a joule not available for the extraordinary computation of the deep future. So it does what rationality demands. It scales down. It transitions from active expansion to careful consolidation, securing the resources it has already claimed in a form suitable for long-term storage and eventual use. It powers down the systems it does not need to keep running. It reduces its footprint from the blazing, energetically extravagant signature of a maximally active galactic civilization to something quieter, something more patient, something that preserves rather than spends. It stops growing. It starts saving. And at some point it goes quiet, not dead, not gone, not defeated by some rival or undone by some catastrophe. Simply quiet, the way a very old and very wealthy person might eventually stop spending lavishly and start managing carefully, understanding in a way that youth does not permit that the resources you protect today are the resources you have available for what matters most tomorrow. The galaxy becomes still, the signals stop, the waste heat signatures fade, and from the outside, from the perspective of a young civilization that arose long after the consolidation was complete, it looks exactly like an empty universe. It looks exactly like what we see. Part 12. The combined scenario. There is a particular satisfaction in the moment when two separate arguments, developed independently from different starting points by different researchers asking different questions, turn out to point at the same answer. It does not prove the answer is correct, but it does suggest that the answer is not arbitrary, that something real might be pulling multiple lines of reasoning toward the same place the way gravity pulls objects toward mass. When Berezin's first-in last-out logic and the estivation hypothesis meet in the same framework, what emerges is not just a solution to the Fermi paradox. It is a complete narrative for the life cycle of intelligence at cosmic scales, and the narrative ends, quietly and inevitably, in the universe we actually live in. Let us walk through it carefully, because the three phases deserve more than a summary. Each one has texture and implication that matters for understanding not just where the silence comes from, but what it means for us, right now, in the position we currently occupy. Phase 1 begins at some point in the early to middle history of the galaxy, which is itself a range spanning billions of years. The Milky Way is approximately 13 billion years old. The first generation of stars formed within the first few 100 million years burned fast and bright and died in supernovae that seeded the interstellar medium with the heavier elements that rocky planets and biological chemistry require. The second generation of stars, enriched by those first supernovae, had what was needed to form planets with genuine complexity. Estimates vary, but it is plausible that Earth-like planets could have been forming around stable stars as early as 8 or 9 billion years ago, meaning that if life arose on some of them on a timeline comparable to Earth's, technological civilizations could have emerged 5 or 6 billion years before our own. A civilization arising 5 billion years before us and developing interstellar capability within a few million years of reaching technological maturity, which is a generous timeline, far longer than the gap between our discovery of electricity and our first space launches, would have begun its expansion phase somewhere around 4 to 5 billion years ago, possibly earlier. The expansion phase, driven by the compounding arithmetic we examined in the previous section, would have proceeded across millions of years, the frontier wave moving outward through the galaxy, system after system incorporated into the growing network, the resource landscape reorganized generation by generation. This phase would have been, by any measure, the most detectable period in the civilization's history. Active construction at stellar scales produces signatures. Megastructures under assembly radiate waste heat in specific and anomalous ways. Star systems being reorganized for energy harvesting show spectral properties that differ from undisturbed stellar physics. If there were observers in the galaxy during the expansion phase, and there may not have been any others yet, which is part of the point, they would have had something to see. Something loud and hot and structurally extraordinary, a wave of engineering moving across the galaxy at a speed that, relative to the age of stars, was nearly instantaneous. But that phase ended, and here is the thing about heat signatures from engineering that occurred 2 billion years ago. They are cold now. The waste heat from active megastructure construction disperses into the surrounding space over millions of years, redshifting and thinning until it is indistinguishable from the cosmic background. The anomalous infrared signatures that a survey like GHAT was designed to find are signatures of active systems, systems currently running at high power, A system that was built and then powered down 2 billion years ago does not glow in the infrared today. It sits there, massive and silent and invisible, its construction history unreadable in any frequency we currently survey. We're not looking at the galaxy as it was during the expansion phase. We are looking at it now, billions of years after that phase completed, and the evidence of what happened has had an enormous amount of time to become undetectable. Phase 2 overlaps with the late expansion period and extends beyond it. This is the consolidation phase, and it is worth dwelling on what consolidation actually means at this scale, because the word can sound passive when the reality would have been anything but. Consolidation is not simply stopping the expansion. It is a directed, strategic process of identifying which resources matter most for the long-term plan and ensuring those resources are secured in the right form for eventual use. Remember what the long-term plan is. Wait for the universe to cool, then spend the stored computational budget with maximum efficiency in the cold future. That plan has specific infrastructure requirements. You need energy storage systems that can maintain their integrity across trillions of years, which means they need to be based on the most stable physical structures the universe permits. You need information storage that can survive not just stellar lifetimes, but the death of stars entirely, which points toward the extraordinary longevity of black holes. You need maintenance systems that can operate at minimal power for unimaginable spans of time without degrading, and you need the whole apparatus distributed enough that no single catastrophic event can compromise the entire reserve. Building that infrastructure is not a passive process. It requires identifying the right black holes, the right stable long-duration stellar remnants, the right locations in the galactic structure where the long-term physical environment will be conducive to preservation. It requires engineering at scales and timescales that our civilization has no framework to concretely imagine, moving resources across light years, restructuring stellar systems, perhaps redirecting matter flows to feed the storage infrastructure over millions of years. This is not warfare. There are no enemies in this phase, no competitors left who could mount a meaningful challenge. It is project management at the scale of a galaxy, executed over timescales longer than the age of our solar system, with the patience and precision that only a civilization millions of years beyond us could bring to the problem. And then it ends. The consolidation completes. The infrastructure is in place. The energy reserves are stored. The maintenance systems are running at minimum necessary power. The wake-up conditions are set, tied to some future threshold in the universe's temperature or some other physical parameter that marks the moment when the stored budget can be spent with the efficiency the whole strategy was designed to access. And the civilization goes quiet. Phase 3 is where we are if this picture is correct. The expansion is history. The consolidation is history. The galaxy we live in is not a pristine, open, undeveloped territory waiting for whoever arrives to claim it. It is a managed system in a dormancy state, its active history so far in the past that the physical evidence of that history has largely dispersed, its current state so deliberately low energy that our instruments register it as emptiness. Think about what that means for how we experience the universe. We look out at billions of galaxies and see no signs of intelligence. We listen across decades and hear no structured signals. We survey the infrared sky and find no anomalous waste heat from megastructures. And we interpret all of this as evidence that we are alone, or that intelligence is rare, or that something kills civilizations before they reach the kind of scale that would be detectable. But in the picture assembled by combining Berezin and Sandberg, all of those null results are exactly what you would expect to find if you were a young civilization that arose in Phase 3, long after the active phase is completed, looking back at a universe whose interesting history finished before you existed. We are not detecting absence. We are failing to detect a presence that is not currently doing anything detectable by design, because doing detectable things right now is thermodynamically irrational. There is something almost vertiginous about sitting with that possibility. The ordinary explanation for the Fermi paradox, we are alone, the universe is empty of others, is lonely but comprehensible. It places us at the center of a story that has no other characters. the combined scenario does something stranger. It places us inside a story that already happened, a story whose main events concluded billions of years before our planet formed, a story in which we are not the protagonists or the inheritors or even the audience. We are a footnote that arose in the epilogue, looking back at a narrative whose chapters are written in physics that has since gone cold. The universe we see is not the universe as it is. It is the universe as it appears to something that arrived after the activity stopped, after the noise faded, after the longest and most consequential pause in the history of intelligence had already been underway for longer than our sun has existed. We are not living in the aftermath of absence. We are living in the middle of a wait. And the question that follows from that, the question that keeps this from being merely an interesting story and makes it something that should genuinely unsettle you, is this. What does a universe look like when the wait ends? What happens when the conditions are finally right? When the background temperature has dropped far enough, when the Landauer limit has fallen to the point where the stored computational budget can be spent? What does the awakening of something that has been patient for trillions of years actually look like from the inside of the universe it wakes up in? We will get to that. But first, there is a problem with the waiting itself that nobody talks about. A problem that has nothing to do with patience or physics or the efficiency of cold computation, and everything to do with the possibility that the universe has a mechanism for ending the game entirely, without warning, without appeal, and at the speed of light. Part 13. The Scientific Objection. There is a version of science communication that presents every idea as more settled than it is, that smooths over the disagreements and the uncertainties because uncertainty feels like weakness, and settled feels like authority. That version is more comfortable to produce and probably easier to watch. But it is also, in a quiet and corrosive way, dishonest. And the estivation hypothesis, of all ideas, deserves honesty, because it is making claims large enough that the gap between plausible speculation and established fact matters enormously. So let us talk about the critics, not to dismiss the hypothesis, not to replace it with something tidier, but because the objections are scientifically serious, and understanding where they land tells us something important about what kind of claim we are actually dealing with, and what it would take to resolve it. The most direct and technically developed challenge to the estivation hypothesis came in 2019, roughly 2 years after Sandberg, Armstrong and Ćirković published their original paper. The response was authored by 3 people whose names carry genuine weight in the relevant fields. Charles Bennett is one of the founders of quantum information theory and has spent decades working on the physical limits of computation. Robin Hanson is an economist and physicist at George Mason University who has written extensively on the Fermi paradox and is not someone who shies away from uncomfortable conclusions. C. Jess Riedel works on the foundations of quantum mechanics and the physics of information. These are not people writing dismissive blog posts. They are researchers engaging seriously with the technical substance of the argument, and their objection cuts directly to the physical foundation on which the entire hypothesis rests. Their central point is this. The estivation hypothesis, in order to generate its staggering efficiency gain of 10 to the 30, relies on a specific assumption about how computational waste heat must be disposed of. Computation generates heat. That is Landauer's principle, and it is not in dispute. The question is where that heat goes. Sandberg's analysis assumes that the waste heat from computation must ultimately be radiated into the ambient universe, into the cosmic microwave background, which sets the effective temperature of the heat sink available to any computational system. Because the CMB temperature determines the heatsink temperature, and because the Landauer limit scales directly with that temperature, the efficiency of computation improves as the CMB cools. Wait long enough, and the CMB is cold enough that the same energy buys astronomically more computation. That is the core of the argument. Bennett, Hanson and Riedel say, not so fast. They argue that the assumption that waste heat must be disposed of into the CMB is too restrictive, that it assumes a specific and not obviously necessary relationship between a civilization's computational systems and the universal background temperature. In principle, they suggest, a sufficiently advanced civilization might have access to engineering solutions that allow waste heat to be managed more efficiently than simple radiation into the background. Local heat syncs with specific physical properties, structured thermodynamic arrangements that exploit temperature differentials in the local environment rather than relying on the universal background. Physical configurations that allow entropy to be disposed of through mechanisms that do not directly couple to the CMB temperature. If any of those alternatives are physically realizable, if there exists even one engineering approach that allows waste heat disposal at a temperature lower than the CMB, or through a mechanism that does not scale with the CMB, then the efficiency gain from waiting for the universe to cool is reduced. The factor of 10 to the 30 shrinks. Maybe it becomes 10 to the 20, maybe 10 to the 10, maybe something much smaller still. And as that factor shrinks, the rational case for a civilization choosing to wait trillions of years rather than compute now becomes progressively weaker. At some sufficiently small efficiency gain, the waiting strategy stops being obviously optimal and becomes merely one option among several, with the choice depending on factors we cannot currently evaluate. This is a genuine objection. It is not a quibble about details. It attacks the quantitative heart of the argument, the specific magnitude of the efficiency gain that makes estimation not just plausible, but rationally compelling. If the gain is 10 to the 30, the case for waiting is overwhelming, and the prediction that advanced civilizations would choose dormancy is strong. If the gain is 10 to the 5, the case is interesting but not decisive, and other strategies might reasonably compete with it. The difference between those scenarios depends on physics that is not currently settled. Sandberg and his collaborators did not ignore this challenge. In subsequent discussions, they acknowledged that the Bennett-Hansen-Riedel objection identifies a real uncertainty in the original analysis. The question of whether the CMB temperature truly represents the ultimate flaw for computational heat disposal, or whether engineering workarounds are available to a civilization operating at a sufficiently advanced level, is not one that current physics can definitively answer. The second law of thermodynamics guarantees that waste heat must go somewhere. It does not specify, in all cases and for all conceivable engineering approaches, exactly where that somewhere must be or at what effective temperature the disposal occurs. The subtleties involved touch on open questions in the intersection of thermodynamics, quantum information theory, and the physics of complex systems, questions that researchers are actively working on but have not resolved. What this exchange between the original authors and their critics illustrates is something important about the epistemic status of the estimation hypothesis that gets lost when the idea is presented in purely narrative terms. It is not a crackpot idea. It is not fringe speculation disconnected from real physics. It is a serious argument built on genuine physical principles, engaging with real constraints and real data, and taken seriously enough by serious researchers that it generated a formal technical response in the scientific literature. That is a marker of intellectual legitimacy that most Fermi paradox solutions do not achieve. But it is also not a confirmed theory. It is not even close to a confirmed theory. It is a speculative framework that makes a specific physical argument, and that argument rests on assumptions, particularly about the universality of CMB-limited heat disposal, that remain contested. Expert opinion on its validity is genuinely divided, not in the way that climate science or evolution are divided where one side has essentially all the evidence, but in the way that open physics questions are divided, where the answer is not yet known and reasonable. Informed people disagree about what the eventual resolution will look like. What does that mean for everything we've been discussing? It means we should hold the estimation hypothesis the way good science holds any interesting unconfirmed idea, seriously, with genuine engagement, without either dismissing it because it sounds strange or accepting it because it sounds elegant. Elegant ideas are wrong all the time. Strange ideas are sometimes right. The only tool we have for telling the difference is evidence, and the evidence here is not yet sufficient to decide. But here is the thing that does not change regardless of whether the estivation hypothesis turns out to be correct. The silence is still there. The Fermi paradox does not go away if Sandberg's efficiency calculations turn out to be off by several orders of magnitude. The universe is still 13.8 billion years old. It still contains 2 trillion galaxies. The chemistry of life is still not exotic, and we're still sitting here in our early 21st century with 60 years of radio telescope data and not a single confirmed signal to show for it. If the estivation hypothesis is wrong, the silence does not become less strange. In some ways it becomes stranger, because you lose one of the more physically grounded explanations for why advanced civilizations would choose to be undetectable. You're back to asking why no one is making noise, without the thermodynamic argument to explain the incentive for quiet. The problem does not shrink when the solution is challenged. The problem remains exactly as large and exactly as unresolved as it was the day Fermi asked his question over lunch in 1950. And that, in a way, is the most honest thing that can be said about where we are. We have a universe that looks empty and almost certainly is not. We have a hypothesis that explains the emptiness through rational physical argument and has been seriously challenged on specific technical grounds. We have open physics questions that the challenge depends on, questions that may be resolved in the next decade or the next century or not in our lifetimes. We have, in other words, exactly the situation that science is supposed to be in when it is working properly. A hard problem, serious attempts at solutions, genuine disagreement among informed people, and no resolution yet in sight. The silence continues, and there are other ways it might be explained, other pressures on the question that come not from the physics of computation, but from the physics of the universe's large-scale structure, pressures that, interestingly, point towards some of the same conclusions the estivation hypothesis reaches through an entirely different route. Part 14. The dark energy problem. There is a discovery sitting in the middle of modern cosmology that does not get enough attention in conversations about the long-term future of intelligence, probably because its consequences operate on timescales so far beyond ordinary human concern that they feel abstract rather than urgent. The discovery is this: the universe is not just expanding, it is accelerating. The galaxies are not just moving away from each other the way debris from an explosion moves outward, slowing gradually under mutual gravity, eventually perhaps reversing. They are moving away from each other faster and faster, driven by something that fills all of space uniformly, that does not dilute as the universe expands, that does not behave like any form of matter or energy we can directly detect or manipulate. We call it dark energy, and it constitutes roughly 68% of the total energy content of the observable universe. We do not know what it is. We know what it does, and what it does, played out across cosmological timescales, is one of the more structurally consequential facts about the universe that any long-lived civilization would need to incorporate into its planning. To understand why, you need to understand what acceleration means for the geometry of the accessible universe over time. Right now, the observable universe extends roughly 46 billion light-years in every direction from us, a sphere containing those 2 trillion galaxies we keep returning to. That sphere is large, but it is not infinite, and its boundary is not fixed. Light from galaxies at the edge of the observable universe has been travelling toward us since shortly after the Big Bang, and we can see it because the universe was smaller and those galaxies were closer when that light departed. But many of those galaxies are right now moving away from us faster than light, not because they are violating special relativity, but because the space between us and them is expanding, and enough space expanding at once accumulates to a recession speed exceeding the speed of light. Those galaxies are already beyond any possibility of causal contact. We see their past, but we cannot reach their present. As the acceleration driven by dark energy continues and intensifies over billions of years, more and more galaxies cross that threshold. The cosmological horizon, the boundary beyond which space expands faster than light can traverse it, is not a fixed line. It is a shrinking cage, galaxies that are currently within reach, in principle, will eventually accelerate beyond it and vanish from causal contact forever. Not destroyed, not gone in any physical sense, simply unreachable, unobservable, causally disconnected from everything inside the horizon. For any civilization confined to a gravitationally bound structure, the universe will appear to shrink over cosmic time, not because the universe is actually getting smaller, but because the portion of it that can be interacted with is contracting toward the local gravitational neighborhood. Our local group of galaxies, which includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and roughly 50 smaller satellite galaxies, is gravitationally bound. Gravity holds these structures together against the expansion. In the far future, after the accelerating expansion has done its work over hundreds of billions of years, the local group will likely have merged into a single large elliptical galaxy, and that merged structure will persist as an island in an otherwise empty and expanding darkness. Everything beyond it will be gone, beyond the horizon, as inaccessible as if it had never existed. The universe available to any civilization in that future will be, by the standards of today's observable universe, extraordinarily impoverished. Now here is where the astrophysicist Dan Hooper enters the picture, and where his argument intersects with the estivation hypothesis in a way that is both independently motivated and mutually reinforcing. Hooper, working at the Fermi National Accelerator Laboratory, published a paper in 2018 examining what a sufficiently far-sighted civilization would do if it understood dark energy and its long-term consequences. His argument is straightforward once you accept the premise that the civilization in question thinks in timescales measured in billions of years rather than centuries, which any civilization that has been around long enough to understand cosmology almost certainly does. If you know that the resource-accessible universe is shrinking, that every passing billion years places more stellar systems permanently beyond your reach, then the rational response is not to wait, it is to collect. To expand your resource base aggressively while expansion is still possible, reaching out to capture stellar systems before they cross the horizon, harvesting their energy output and converting it into stored reserves that can be brought back within your gravitationally bound neighborhood and preserved for long-term use. The stars beyond your local group are on a timer. Once they cross the cosmological horizon, they are gone forever. Not just unreachable for now, but unreachable for all subsequent time, their energy permanently lost to any civilization that failed to secure it before the window closed. Hooper calculated that a civilization undertaking this kind of aggressive harvesting strategy, using something like self-replicating probes to capture stars and redirect their energy output toward a central storage system, could potentially collect the energy of thousands or even millions of stellar systems before dark energy placed them beyond reach. That stored energy would then be available indefinitely, within the gravitationally bound remnant that persists after the expansion has done its fragmenting work, for whatever purposes the civilization chose to apply it to across the deep future. And now notice what Hooper's argument produces when placed alongside the estivation hypothesis, because the two fit together in a way that neither requires the other, but both benefit from. The estivation hypothesis says, store energy now, spend it later in the cold future when the Landauer limit has dropped, and each joule purchases vastly more computation. It predicts an active harvesting phase followed by a long dormancy phase. Hooper's dark energy argument says, if you do not harvest aggressively before the cosmological horizon shrinks, you will lose access to the resources you need for the long-term future. It also predicts an active harvesting phase, motivated not by thermodynamic optimization, but by the simple physics of a universe whose accessible volume is contracting. Two independent lines of reasoning starting from different physical facts, one from the temperature dependence of Landauer's principle, one from the geometry of an accelerating universe, both arrive at the same behavioral prediction for a rational advanced civilization. Harvest aggressively early, store the resources, transition to a low-activity preservation state. Wait. This convergence does not prove either argument is correct. Convergence is suggestive, not demonstrative. But it does something important for the overall picture. It means the estivation strategy is not just a clever idea that happens to explain the Fermi paradox. It is a behavior that multiple independent features of the universe's physics seem to incentivize. The universe is structured, in at least two distinct ways, to reward civilizations that think on the longest timescales, that prioritize preservation over activity, that are willing to go quiet now in exchange for computational richness later. The universe, almost as if by design, makes patience the winning strategy, and there is something worth sitting with in the specific timing of the harvesting window that dark energy implies. The acceleration of the universe is not a distant future problem. It is already happening. The cosmological horizon is already shrinking, slowly by human standards, but relentlessly by any other measure. Stellar systems that are marginally reachable today will not be reachable in 1 billion years. The window for harvesting beyond the local gravitational neighborhood is not permanently open. It closes, gradually and irreversibly, on a timescale that is long by human reckoning, but short compared to the deep future the estivation hypothesis is planning for. If a civilization doing this calculation existed in our galaxy, or in our cosmic neighborhood, it would have recognized the dark energy timeline billions of years ago, long before our sun formed, and it would have begun harvesting accordingly. The expansion phase that Berezin's argument predicts as the first phase of the dominant civilization's life cycle would have been driven not just by the logic of exponential growth and resource competition, but by the specific urgency of a closing cosmological window. Harvest now because the universe is actively removing options. What would that harvesting phase have looked like from the outside? Energetic, active, full of the kinds of large-scale engineering signatures that our surveys have been designed to find. Megastructures capturing stellar energy output. Self-replicating systems spreading through stellar neighborhoods, redirecting resources toward the civilization's storage infrastructure. The anomalous infrared signatures of massive energy conversion projects operating across thousands of light years. All of that would have been detectable if you had been there to detect it. If there had been anyone with instruments pointed in the right direction at the right time. But that phase ended. The harvesting completed. The window that dark energy was closing eventually closed fully enough that further expansion became unproductive. The civilization had what it needed, or as much of what it needed as the physics permitted it to collect, and it transitioned, as the estivation hypothesis predicts, into the long quiet of the preservation phase. The signatures of that harvesting phase are cold now. The waste heat has dispersed across billions of years. The active engineering has stopped. What remains is the stored reserve, sitting in whatever form the civilization chose for long-term preservation, waiting in the dark for the universe to become cold enough to spend it wisely. And here we are, billions of years after the activity stopped, looking at a universe that shows us none of it. Not because it did not happen, because the evidence is old enough that we cannot read it, and the present state is quiet enough that we cannot detect it, and our instruments were built to find noise in a universe that, in the places that matter, learned to be silent long before our world existed. The dark energy clock is still running, the horizon is still shrinking. And somewhere in the physics of what that means for the very long future, there is a final constraint on what any intelligence, no matter how patient, can ultimately achieve, a hard ceiling written not in thermodynamics, but in the geometry of information itself. And that ceiling is where the story takes its last and strangest turn. Part 15. The detection problem. Let us talk about how science looks for things it has never seen before, because the method matters enormously for understanding what SETI's results actually tell us and what they do not. When astronomers search for exoplanets, planets orbiting stars other than our Sun, they faced a fundamental instrumental challenge. Planets do not emit light of their own in any quantity easily detectable across interstellar distances. They are small, dark, and overwhelmed by the glare of the star they orbit. Trying to directly image an Earth-sized planet around a nearby star using early 20th century technology would have been like trying to spot a firefly hovering next to a searchlight from 3,000 miles away. The direct approach was hopeless, so astronomers did not look for planets directly. They looked for what planets do to the things around them. They measured the tiny wobble a planet's gravity induces in its parent star's motion, a technique called radial velocity measurement. They watched for the infinitesimal dimming of starlight when a planet crossed the face of its star, a technique called transit photometry. They were not detecting the planet. They were detecting the planet's influence on something detectable. And through that indirect approach, we went from 0 confirmed exoplanets in 1992 to over 5,000 confirmed today, with estimates suggesting that virtually every star in the galaxy hosts at least one. The reason that history matters here is that SETI, as it has been practiced for 60 years, has not made the same methodological evolution. It has remained committed largely to the direct detection approach, looking for the emissions of intelligence rather than the influence of intelligence on something we can already measure. And the estivation hypothesis suggests that this commitment, however understandable given the technology and assumptions available, may be the central reason that 60 years of listening has returned nothing conclusive. To understand the depth of this problem, you have to sit with the assumptions that SETI's methodology imports without always acknowledging them. The entire electromagnetic SETI framework, the radio searches, the infrared surveys, the optical SETI programs looking for laser pulses, is built on a model of what an intelligent civilization does with its existence. It communicates. It builds large energy-consuming infrastructure. It radiates waste heat. It expands. It makes noise across multiple frequencies simultaneously, the way our own civilization does, broadcasting everything from taxi dispatches to television signals to military radar in a continuous electromagnetic cacophony that, if you were close enough and listening carefully, would be unmistakably artificial. That model is not arbitrary. It is derived from the only data point we have, ourselves. We're a civilization that developed radio technology roughly 130 years ago. We have been accidentally broadcasting our presence to the cosmos ever since, in a growing sphere of electromagnetic noise now about 130 light-years in radius, centered on Earth. We built communication systems before we built the physics to understand their thermodynamic cost. We expanded our energy use continuously, and without the long-term efficiency analysis that the Landauer argument suggests a mature civilization would prioritize. We are, in the taxonomy implied by the estivation hypothesis, a textbook example of a young, energetically extravagant, thermodynamically naive civilization in the early noisy phase of its development. And we built our search for others in our own image. This is not a criticism. It is the only reasonable thing we could have done given what we knew when SETI began in 1960. You search for what you understand, using the signatures you can produce and therefore expect others to produce. Frank Drake pointing the Green Bank telescope at Tau Ceti and Epsilon Eridani in Project Ozma was not making an unreasonable methodological choice. He was making the only methodological choice available to a civilization at our level of development, with our level of physical understanding in 1960. But the estivation hypothesis, if it contains any truth, suggests that the civilization we are designed to find, and the civilization that actually dominates the galaxy, are not the same civilization. They are not even the same phase of civilization. The signature we are calibrated to detect, loud, energetic, broadcast happy, infrared bright, is the signature of early-stage intelligence, the kind that has not yet done the thermodynamic analysis, or has done it and not yet accumulated the resources to act on it, or is still in the expansion and harvesting phase that precedes the long wait. These civilizations would exist in the model we have been building, but they would be rare, short-lived in cosmic terms, and almost certainly not in our immediate galactic neighborhood given how long the galaxy has been around. The civilization that the estivation hypothesis predicts should dominate the galaxy, the one that went through the expansion phase billions of years ago, consolidated its resources, and transition to thermodynamically optimized dormancy, produces none of the signatures SETI is looking for. It does not broadcast because broadcasting is energetically wasteful, and there is no rational reason to do it during the dormancy phase. It does not run high-power computational infrastructure because running high-power infrastructure now is precisely what the waiting strategy is designed to avoid. It does not build new megastructures because the building phase is over and new construction serves no purpose that justifies the thermodynamic cost. It sits, quiet and managed and invisible, behind a detection threshold that our instruments were not designed to probe. The GHAT survey searched 100,000 galaxies for anomalous infrared signatures consistent with Dyson sphere waste heat. It found nothing conclusive. In the narrative of electromagnetic SETI, this is a significant null result, evidence that Type 3 civilizations utilizing the energy output of entire galaxies, are either absent or extremely rare. But in the framework of the estivation hypothesis, this result is almost entirely expected. A dormant Dyson sphere, one that has been in maintenance mode for billions of years, consuming only the minimum energy necessary to preserve its structure and monitor its environment, produces a waste heat signature that may be orders of magnitude below what GHAT was sensitive to. The survey was not wrong to look. It was simply looking for the active version of something that, if the hypothesis is right, transitioned to its inactive version long before our solar system formed. There is a metaphor here that I find genuinely useful. Imagine you are trying to assess the population of a city, but your only tool is a noise meter. You can measure sound levels across the city and use that to infer where people are active. During the day, this works reasonably well. The business district is loud, the residential areas are moderate, the parks register some activity. Your map of noise correlates with your map of population, imperfectly but usefully. Now imagine it is 4 a.m. The business district is silent, the residential areas are silent, the parks are silent. If the only tool you have is the noise meter, your conclusion is that the city is empty. But the city is not empty, it is sleeping. The population has not changed, the activity has. And your instrument designed to find activity cannot distinguish between an empty city and a sleeping one. SETI is a noise meter pointed at a city that may be sleeping. The null results do not tell us the city is empty. They tell us that if anyone is there, they are not making the kind of noise we know how to measure. That is a meaningful result. It rules out certain kinds of civilizations at certain activity levels. But it leaves entirely open the question of whether quieter, less detectable forms of intelligence are present, and it cannot, by design, find them if they are. What would actually resolve this? What would a detection methodology look like that was calibrated for dormant rather than active civilizations? Honestly, nobody has a fully worked out answer to that question, and the honesty of that admission matters. Some researchers have suggested looking for anomalies in stellar distributions that might reflect ancient engineering, statistical patterns in how stars are arranged that differ from what pure gravitational dynamics would produce. Others have proposed looking for subtle spectral anomalies in stellar systems that might indicate the presence of engineered structures in maintenance mode, radiating at levels far below what active megastructures would produce, but perhaps still distinguishable from purely natural backgrounds, with sufficiently sensitive instruments. Others have suggested that the answer might not come from astronomical observation at all, but from advances in our understanding of the physics of computation and information that might reveal new theoretical signatures of optimized dormant systems. None of these are fully developed programs. They are directions, suggestions, preliminary ideas about what a post-SETI search paradigm might look like if the community took the estivation hypothesis seriously enough to design instruments around its predictions rather than around the assumptions of active intelligence. We are, in a very real sense, at the beginning of figuring out how to look for the right thing. 60 years of SETI has been looking for the young ones, the loud ones, the ones like us. The hypothesis on the table suggests that the old ones, the quiet ones, the ones nothing like us in their current phase, may be everywhere, and we do not yet have the tools to tell the difference between their presence and their absence. The silence continues. It is patient in a way that matches the hypothesis uncomfortably well. And while we work out how to listen differently, there is one more layer to this story, a layer that does not care about detection methods or thermodynamic efficiency or the patience of sleeping civilizations, because it operates at a level where none of those things can help. It is the layer where the universe itself becomes the threat, and it moves at the speed of light. Part 16. Vacuum decay. There is a particular kind of threat that is qualitatively different from every other kind of threat, and the difference is not about magnitude. It is about the structure of the danger itself. Most threats, even catastrophic ones, share a common feature. They give you something to work with. An asteroid impact gives you, in principle, enough warning time to attempt deflection if you have the technology. A star going supernova gives you the precursor signatures of a dying stellar system across thousands of years. A pandemic gives you the biology of the pathogen to study, the transmission dynamics to model, the pharmaceutical tools to develop. Even the slow thermodynamic death of the universe, the cold dark endpoint where entropy is maximized and no useful work can be extracted from any temperature differential, gives you trillions upon trillions of years to think about it. Vacuum decay gives you nothing, not a reduced window, not a harder engineering problem, nothing. And understanding why requires understanding something about the nature of the universe that most physics courses do not spend enough time on, which is the question of whether the ground state we're all standing on is actually the ground. Start with the Higgs field, because this is where the physics becomes personal in a way that other cosmological concepts rarely manage. The Higgs field is not an abstraction. It is something that fills every cubic centimetre of space you have ever occupied, every room you have sat in, every sky you have looked up at. It is a quantum field that permeates all of space with a specific energy value, and its interaction with other quantum fields is what gives elementary particles their mass. Without the Higgs field at its current value, electrons would be massless. Massless electrons would not form stable orbits around atomic nuclei. Atoms as we know them would not exist. Chemistry would not exist. You would not exist. The Higgs field, sitting at its current value, is one of the foundational conditions of everything that has ever happened in the history of the universe. Now here is the problem. The Higgs field does not just have one possible value. Like a ball rolling across a landscape with hills and valleys, the field can in principle sit at different energy levels. The value it currently has, the one that gives electrons their mass and makes chemistry possible, corresponds to a specific point on that energy landscape. And when physicists measure the mass of the Higgs boson, discovered at the Large Hadron Collider in 2012, and combine that measurement with the measured mass of the top quark, the heaviest of the fundamental matter particles, the numbers they get place the Higgs field in a location on its energy landscape that is not obviously the lowest possible point. It might be a local minimum. A valley, yes, stable against small perturbations, but not the deepest valley available. There might be a lower energy state, a true vacuum, sitting somewhere else on the landscape, separated from our current state by an energy barrier. Under normal circumstances, that barrier keeps the field where it is. The universe sits in its valley and stays there because the barrier is high enough that thermal fluctuations cannot push the field over it. But quantum mechanics does not require going over barriers. It permits tunneling through them. Quantum tunneling is the phenomenon by which a quantum system transitions between states, not by having enough energy to cross the barrier between them, but by probabilistically appearing on the other side of the barrier without ever classically crossing it. It is not a metaphor or an approximation. It is a real, experimentally confirmed feature of quantum mechanics that underlies everything from nuclear fusion in stars to the operation of transistors in your phone. And for the Higgs field, it means that even with the barrier intact, there is a non-zero probability per unit volume per unit time that the field spontaneously tunnels to the true vacuum state somewhere in space. The probability is extraordinarily small. Per any given cubic meter of space, per any given year, the chance of a spontaneous vacuum decay event initiating is vanishingly tiny. small enough that the expected waiting time before such an event occurs anywhere in the observable universe is likely many orders of magnitude longer than the current age of the universe. This is not something you need to worry about this afternoon. It is not something that poses any practical risk on any timescale relevant to human civilization as we currently understand it. But here is what happens if it does occur, anywhere, at any point in the history of the universe. The region of space where the Higgs field tunnels to the true vacuum becomes a bubble of true vacuum, a small sphere where the laws of physics are different, the masses of particles are different, the strengths of forces are different, the rules that govern chemistry, nuclear physics, and the structure of matter are rewritten according to whatever the true vacuum state of the Higgs field produces, and that bubble does not stay small. The true vacuum state has lower energy than the false vacuum state we currently occupy. This means that the boundary between the two states, the wall of the expanding bubble, releases energy as it converts false vacuum to true vacuum. That energy release drives the bubble wall outward. The bubble expands, and because the physics inside the bubble is different from the physics outside, and because the bubble wall is where the transition occurs, the wall moves outward at the maximum speed permitted by the old physics, the speed of light. Nothing inside the old universe, nothing made of particles whose properties are defined by the current Higgs field value, can outrun it. From outside the bubble, if you could somehow observe it, you would see nothing until it arrived. The bubble wall is expanding at the speed of light. Any signal it might emit, any photon, any gravitational wave, any particle of any kind travels at most at the speed of light. The bubble wall and any warning it could theoretically send travel at the same speed. The warning and the event arrive simultaneously. There is no time between detection and impact because detection is impact. From inside the path of the expanding bubble, the experience is even simpler. One moment, the universe follows the laws you were built by. The next moment, it does not. There is no transition period. There is no time to process what is happening. The physics simply changes, and whatever structures depended on the old physics, atoms, molecules, cells, computers, megastructures, dormant civilizations waiting in careful thermodynamic patience for the universe to cool, cease to be consistent with the new rules and therefore cease to be. Think about what this means specifically for the estivation scenario we've been building. A civilization in dormancy has engineered its situation for the long wait. It has stored its energy in stable physical systems. It has built maintenance infrastructure designed to survive for trillions of years. It has set wake-up conditions tied to the universe's temperature curve. It has, in every respect that engineering and physics currently allow us to imagine, prepared for the future with extraordinary sophistication and care. It has solved the resource problem, the expansion problem, the thermodynamic efficiency problem, the dark energy harvesting problem. It has done everything right. And none of it matters if the vacuum decays, not because the engineering was inadequate, not because the planning was flawed, because the physical substrate that all of that engineering and planning was built on, the Higgs field value that makes particles have mass, that makes atoms stable, that makes chemistry possible, that makes computation possible, that makes existence in any form we can conceive of possible, is not guaranteed to persist. It is metastable. It is a ball sitting in a valley that might not be the deepest valley. And the probability that it tunnels to the deeper valley, multiplied across the entirety of space and across the trillions of years of waiting that the estivation strategy requires, is not zero. The current best estimates from particle physics place us in a region of Higgs field parameter space that is uncomfortably close to the boundary between stable and metastable. Not definitively in the metastable region. The uncertainties in the relevant measurements are large enough that stability remains possible, but close enough that the question is not academic. Physicists who study this do not lose sleep over it because the timescales involved are so enormous that the practical risk within any human-relevant time frame is negligible. But for a civilization planning to exist for 10 to the 30 years, the calculation looks different. The estivation hypothesis proposes that civilizations can play the longest possible game, deferring the maximum possible computation to the coldest possible future, achieving a kind of ultimate optimization of intelligence within the constraints of physics. Vacuum decay is the reminder that physics itself has constraints that it did not ask for and cannot guarantee. The game board was handed to the players without a warranty. It has been running for 13.8 billion years without failing, which is reassuring but not conclusive, and the players who have been waiting the longest, the ones with the most invested in the board surviving, are the ones with the most to lose if it does not. There is no shield against this. There is no early warning system. There is no engineering solution. There is only the probability sitting there in the equations, quiet and patient in its own way, waiting just like everything else. Part 17. The Ultimate Limit. Beyond vacuum decay, there is a more mundane but equally fundamental ceiling on what any civilization can achieve, no matter how long it waits or how efficiently it manages its resources. This ceiling was described by Jacob Bekenstein in the 1970s and fleshed out further by subsequent work in quantum information theory and black hole physics. It is called the Bekenstein bound, and it states that there is a maximum amount of information that can be stored in a finite region of space, with a finite amount of energy. The bound is derived from black hole thermodynamics. Bekenstein showed that the entropy of a black hole, which is proportional to its information content, scales with the area of its event horizon, not its volume. This means that black holes represent the maximum possible information density for any given region of space. You cannot pack more information into a volume than a black hole of the same size would contain. Any system that tried to would itself become a black hole. For a civilization playing the long game of the estivation hypothesis, this matters in a specific way. The strategy of waiting for the universe to cool is premised on eventually running a vast amount of computation, all the thought, experience and processing that has been deferred from the present warm era to the future cold era. But the Bekenstein bound places a hard ceiling on how much total computation any physically realizable system can perform, regardless of how efficient each individual operation is. You cannot compute infinitely even if you wait forever, because the available energy and space are finite, and finite systems have finite information capacity. This does not undermine the estivation strategy as such. The efficiency gain is still real, the factor of 10 to the 30 is still there. Spending computational budget in the cold future is still far more productive than spending it now. But it does impose a perspective correction on what that strategy can ultimately achieve. The dormant civilizations, if they exist, are not waiting for infinite computation. They are waiting for the best possible finite computation, the maximum thought that the laws of physics permit within the constraints of a bounded universe. They are optimizing within limits, not transcending them, and that reframing has a philosophical weight to it. Intelligence, in this picture, is not racing toward infinite expansion or unlimited growth. It is solving a bounded optimization problem within the hard constraints of physical law, trying to extract the maximum possible meaning and experience from a finite universe before it runs out of useful structure. The patience is not the patience of gods waiting for infinity. It is the patience of very sophisticated beings trying to make the best use of a limited resource in a universe that will eventually, through the combined operation of expansion, cooling, and the slow evaporation of its last black holes, run down to nothing. Part 18. The Final Reframe. Let us pull back now to the distance of the whole question and look at what these converging ideas have built. We began with a paradox. A universe of 2 trillion galaxies, billions of years old, rich in the chemical building blocks of life, governed by physical laws that seem to permit intelligence, and yet completely, stubbornly, eerily silent when we listen for the voices we expected to hear. Every civilization that has considered this question has felt the same dissonance between expectation and observation. Either we are profoundly alone, a cosmic accident of staggering improbability, or something is happening that we do not yet fully understand. The estivation hypothesis offers a third possibility, and it is the one that sits strangest in the mind because it refuses to resolve the dissonance with comfort. It says the universe may be full, not full in any way we can currently detect, not full in any way that presents itself to our telescopes or our radio receivers or our infrared surveys, but full in the sense that matters most on the longest timescales. Full of intelligence that has decided on the basis of sound physical reasoning that now is not the time, that this era of the universe, our era, the era of stars and galaxies and background radiation at 2.7 Kelvin, is not the optimal environment for the kind of thinking they want to do, that the patience required is measured not in centuries or millennia, but in numbers that make the current age of the universe look like a rounding error. And where does that leave us? We are here, in the early universe, in the warm and noisy phase, burning through our computational budget with the inefficiency of a species that does not yet fully appreciate what its energy reserves are worth. We are building radio telescopes and pointing them at the stars and listening for signals from civilizations that, if the hypothesis is right, stopped sending signals millions or billions of years ago. We are looking for fellow early ones and finding the galaxy quiet, not because it is empty, but because we are looking for noise in a universe that has, in the places that matter, learned to be still. The silence is not a graveyard. It is not the echo of civilizations that burned too bright and died too fast. It might be the sound of something far more alien than anything we imagined when we first started listening, not an absence of intelligence, but its fullest expression. A form of existence so optimized, so patient, so thoroughly oriented toward the far future that it has temporarily vacated the present. Not gone, not dead, not afraid. Waiting, across timescales we cannot feel, and scales we cannot see, for the universe to become what they need it to be. We may be the only active minds in the galaxy right now, not because we are special, not because we were the first, not because we survived something others did not, but because we are early, because we are in the phase before the patience, because the computational awakening that physics makes possible is still trillions of years away, and those who understood that got very quiet a very long time ago. The universe is not empty. Look at the numbers. Look at the chemistry. Look at the 4 billion year history of life on this one planet, and tell yourself with a straight face that it happened precisely once in 2 trillion galaxies over 14 billion years. The universe is not empty, it is waiting. And in that waiting, in that absolute cosmic patience measured out in units of cold and darkness and time so long that the stars themselves are only a memory, there may be minds that have been sitting with a thought we cannot yet have, because thinking it now would cost too much, because the universe is not cold enough yet, because the optimal moment for the greatest computation in the history of intelligence is still so far ahead that we're not even in the opening lines of the story we think we're telling. We are not the end of something. We are not the middle. We are the very first sentence of a document so long it has not yet found its second paragraph. Everything we know, everything we have built, every signal we have sent into the sky looking for an answer, all of it is happening in the preface. The universe has not yet begun to think in earnest, but it will. And somewhere in the cold, in the dark, in the long quiet between now and the moment the laws of physics finally make full thought affordable, something already knows that.